this is perhaps closest to what you're going to implement in practice in many problems. The topic is called linear quadratic optimal control. And it starts with a very simple motivation. We know state feedback control is powerful. We know it can place, as long as the system is controllable, then we can place arbitrarily the closed loop eigenvalues. The design of these eigenvalues, however, people used to call it an engineering art, because you have to choose based on your system dynamics. You have to figure out what kind of eigenvalues will be suitable for the closed loop system. And in the past, it has been manual in the state feedback control algorithm design. Sometimes it just gets easier that if we can make the performance just a little bit more explicit. Here, if we manually place the eigenvalues, then the performance is implicit. We think about what kind of closed loop dynamics we want. We think about how fast the errors should converge to zero. Then we assign these eigenvalues to induce this proper error convergence. The LQ, linear quadratic optimal regulation control, or sometimes known as simply LQ regulator or LQR, it doesn't specify the closed loop poles. The performance is explicit in the sense that we know exactly what we want to achieve right at the beginning of the problem. We assign a so-called performance index at the beginning of the problem. What we're going to do today is to formulate the problem properly and then introduce two classes of LQ controls. One is the finite-horizon LQ control problem. Another is the infinite-horizon LQ control problem. The goal is as follows. When we talk about the performance index, this is the performance index that we mean. We say, given an n-dimensional state space system, x dot equals ax plus bu, y equals cx with some initial conditions, the system can be multiple input and multiple output. It can have R inputs and M outputs, no problem. The problem of LQ treats them equally well. They all try to minimize this cost function. It reads as follows. It contains something about the terminal time, TF. So this is an explicit term that we want to reduce, want to minimize related to the terminal condition of the system. And then it contains some transient regulations from some initial time t0 to terminal time tf. And inside we have something related to both the states in this period of time as well as the input in this period of time. More specifically, here are some assumptions to make the problem well posed. First of all, we say these Q, R, and S, these are at least positive semi-definite. S should at least be positive semi-definite, Q should be positive semi-definite, and R should be positive definite. These conditions are similar to the conditions that we want to minimize in the single input, single output case, quadratic cost function where the coefficients are positive, or at least non-negative. They assure a non-negative cost and a well-posed problem, these conditions. And this terminal cost over here penalizes the deviation of the state from the origin at TF. We want to make x to be close to 0, and we don't want to use a lot of control efforts. We want to use, if possible, the minimum amount of control efforts. Here, in this integral, we talked about this terminal cost. Inside this integral, x transpose qx, it penalizes the transient. And then often, we say if we select q to be c transpose c, this is a positive semi-definite matrix by construction. Then this transient cost will equal to, if q is c transpose c, then we have y transpose times y over here. And this performance index directly minimizes the output during this transient period of time. But Q can be other things as well, so it's not exclusive that Q has to be C transpose C. Finally, this U transpose RU term inside this integral, it will penalize large amounts of control efforts. So those are the conditions. This is the finite horizon continuous time LQ problem. When we say, I just want to consider everything from a starting time to the end of the system operation, then we say the control horizon is made infinitely long, TF will go to infinity. Then this problem reduces to the infinite horizon LQ problem, starting from some initial time and then to infinity in this integral. Something changes in this from here to here. You can see we no longer require this terminal cost, because for this cost function, for this performance index to make sense, it will turn out that x will have to be 0 at a steady state. We cannot have a non-zero state in the end, because if anything that's non-zero, if you integrate it over time, then it's going to be infinity. It's going to have unbounded cost function. So that's the first condition. Terminal cost is no longer needed. The control will have to drive x to the origin. And often we say the initial time, we just let it to be 0. Then the integral is from 0 to infinity, and the performance index reduces to this most common form over here. So that's the problem formulation. Now let's solve the problem. Let's consider both the finite horizon problem and the infinite horizon problem, also sometimes called stationary LQ problem. The finite horizon problem started with, again, this performance index. Everything is finite. The time, T0, Tf, these are all finite values. We have the system dynamics. We have S, R, and Q as follows. Here, Q is written as C transpose times C. The solution to this type of integral is actually no longer so unfamiliar to us. In the Lyapunov analysis, we have these kind of quadratic functions. And if we do, let's try with a Lyapunov-like construction. Let's say V is half of X transpose Px. Well, P is a symmetric matrix. Let's do this construction. And then let's talk about the derivative of this Lyapunov-like function. It turns out once we take the derivative of it, then we will be able to combine some term from this derivative function with those terms inside here. The details are as follows. The first thing to notice is if we take the derivative of this v function, we need to consider 3 terms. The 3 terms inside this product, they all depend on time. So chain rule requires us to take the derivative of the first term plus taking the derivative of the second term, and then plus taking the derivative of the last term. So slightly different from the stability analysis, where this P in the Lyapunov function analysis is constant, so we don't have this extra term. But here, we have it here, because this is not an infinite integral. Once we do that, this is very similar. We have the x dot is ax plus bu, similar to the Lyapunov analysis. And on the right-hand side over here, x dot will also introduce an ax plus bu term. In the middle, we haven't said anything about p yet, so the root of p remain in this middle term. Once we do that, we can see that there are lots of quadratic terms. Ax over here, once it takes the transpose, it will produce a quadratic term of x transpose A transpose P times x. That's the first term over here. And then similarly, on here, on the right-hand side, we have X transpose PAX. So X transpose PAX. And then in the middle, we have another quadratic function about X as well. Then this 3 will constitute the quadratic term about X. And in the remaining, we have some cross-product term that relates to BU. After the transpose, it becomes U transpose B transpose PX. And then over here, we have X transpose PBU over here. Now, if we do this, and then consider this usual integration, we take the integration of the derivative we just calculated from the initial time t0 to the terminal time tf. Then we know, without just from calculus, this integral equals v tf minus the value of v at initial time t0. So this is just from calculus by definition. And then on the right-hand side, we just bring in the derivative we just calculated. We already saw, derivative contains a lot of quadratic terms about x, contains cross-product term between u and x, and then do the integral over here. Now, add this performance index to this obtained equation that contains also an integral from t0 to tf. We can have some quadratic functions that becomes very easy to handle. More and more quadratic terms will appear. You can see on the right-hand side, this integral will become, we have quadratic terms about x, quadratic terms about x. They add together will give a new quadratic term about x, where this matrix inside is A transpose P plus PA plus this Q plus dP over dt. The cross-product terms will remain over here. And finally, there is a quadratic term about the input u. That's everything in this integration. And then the remaining, we just copy them down from here. We have j on the left-hand side of the equation added to this part, v of tf minus v of t0. And then on the right-hand side of this equation, we have a remaining term that relates to the terminal cost, and it just moves to here directly. All right, the last item to do is something that the concept we all know from even perhaps middle school, high school. We just do this complete of squares. You can see here we have a quadratic term about u, and we have a cross product term between u and x. In the scalar case, things are looking much easier. Let's start from there to build the intuition. In the scalar case, u is a scalar, r is a scalar, x is a scalar, pbu, they all are scalars. This reduces to r times u squared plus 2 times x pbu. It's 2 because x pbu here is equal to u bpx if everything is a scalar. So, you know, actually completing the squares is very easy for this one, right? We have a quadratic term about u is actually square root of r, u squared. And then over here we have 2 times the square root of r times u times pbx or bpx. I want to write it slightly differently. In the scalar case, actually they are equal, but for consistency, I can write it this way. So inside over here, we have 2, this term is equal to 2 times square root of r times u times pbx, and then I need another square root of r inverse or simply I need a r to the power of -1/2 to make it equal. If you see that, then the problem is half done, because now I can add and subtract terms. I can add and subtract the square of this term over here, so that the first 3 terms, you can see over here, becomes a big square term. You can see that taking the power of this one will directly generate this first 3 term in the second line of the equation over here. That is the scalar case. Just to complete the squares, then we can have this becomes a square term minus another square term. The general case where these are matrix or vectors is similar. You can do this, complete the squares, and have the following result over here. This, in the vector case, it becomes the norm of inside this matrix vector multiplication. Here, the 2 norm means if I have a vector A, then the 2 norm of the vector is just the A transpose times A. So this is this term transpose times itself. Then you can see a lot of transpose term will appear. That generates our U transpose, B transpose, etc. And then this term, in the vector case, it becomes, again, a norm, which is this vector is transpose times itself. So here, taking the transpose of this vector and then times itself, then you have this term. If you see that, then the problem becomes somewhat obvious. If you do the completed squares, we said this cross product term and this quadratic term about U is nothing but a 2 norm, a quadratic term again, and then minus another quadratic term. Bring these all together inside here, we are going to have this first 4 terms in this matrix will remain. And then we have a new quadratic term about x. We'll go into here, and it's a minus sign. And finally, we have another square term that relates to U. Now look at this one. Can someone tell me what is the best we can do to minimize this huge chunk of integral? We know both of them will be positive, at least non-negative, right? Because they are all quadratic terms. Take the derivative with respect to U, okay? That's one proposal. Anything even less computational? We know this one is non-negative. The best we can do in terms of designing R is, in terms of designing U is what? Just make this whole thing to be 0. That's the best I can do, right? So if you recognize that point, then you can see the best. I'm just copying down the equations here again. And you can see the best that the control can do in minimizing the cost is to have 3 things. First is this that we talked about. Make this to be 0, which gives us this control law. You can see if control law U equals negative of R inverse times B transpose PX, then it's going to cancel out everything in this part. So that's the good news. This is 0 now. And second is, what if everything inside here just becomes 0? That will be fantastic. The best scenario for the other term in this integral is that if this P matrix somehow its derivative is the negative of everything in here, then that will be fantastic. And lastly, we have something else too. We have the terminal cost on the right-hand side over here. And on this side, we have this VTF that remains over here. And the best that we can do in assigning P at TF is if we can cancel this one out directly, then the J term will become, so everything here goes away, goes away, goes away, goes away. J will equal to half of the initial condition times P at the initial time and Px0. That is the best or simplest result that we can get from this large equation. And it makes, we have the freedom. This is the best we can do, this is the best we can hope. And in the meantime, we do actually have the freedom. Why? We have the freedom to choose our control input U, right? And we also have the freedom to choose P. Because remember, a few slides ago, when we introduced P, did we make any assumptions about, did we make any conditions for P to satisfy? No, right? We only said we want P to be symmetric. So, it is actually possible to make these conditions to hold too. Let's now look at this result. It's actually a fantastic result. We have an optimal control law, and we have a matrix equation that we need to satisfy. The optimal control law, if you take a look at the structure, U is negative R inverse B transpose PT X, is actually a state feedback law. U depends only on the state X. So that reflects the power of feedback control, right? We already said state feedback can place the eigenvalues anywhere we want. This control law actually places the eigenvalue at those locations that will directly minimize the performance index. And this is a time-varying control law because P here depends on time. It has to actually satisfy an equation over here. It's a time-varying control law, and the closed loop is actually time-varying because if you substitute U in here, then we have a PT in this closed loop A matrix. So we started with some performance index, and it turns out, without much effort, we derived at a time-varying control law that is very easy to implement and easy to understand. So time-varying doesn't mean it's more complicated. This is a time-varying law, control law. Now, the second observation is let's focus a little bit more on this matrix equation that P matrix should satisfy. This is called the Riccati differential equation. It's a differential equation because it has derivative of P on the left-hand side. It can be actually solved numerically. This Riccati equation, we know that when solving differential equations, what we need to know some boundary conditions, right? In here, we know actually the boundary condition for the P. This is given at the final time, TF. And then we can solve this differential equation. If we have an initial time and the differential equation, we can integrate forward in time. And if we know the terminal time, final time of a differential equation, we can solve it by integrating backward in time. Now, you might feel it a little bit unnatural, but it's actually no more than a forward integration itself. Because if you do a change of variables, if you change P to be P star TF minus T, then PTF, after this change of variable, becomes P star TF minus TF has to equal to S. So we have an initial value for P star. And then in here, we have the negative of dp. Because t is here and we have a negative t here, we know that p dot is equal to negative p dot star. So on this side, actually, things become also easy. We don't have a negative sign. We just have a derivative term. So therefore, this backward integration of the Riccati differential equation is actually a forward integration. We know the initial time. We do integration. We know the slope in the sense, right? We know the slope of what P star is going to become in the next time instance. Then we just integrate forward in time. So that's actually fantastic. Not only do we have a state feedback law, but also we can actually solve this Riccati equation. In MATLAB, we can solve this numerically by, for example, ODE 45. And I have some examples, actually, I will show you in a minute. Before I show you that example, let's do a final observation. The minimum performance index, J naught, is a function of the initial state x, t, 0, and then the value of p at time t, 0. We know right at the beginning when we introduced this S, we talked about S has to be positive semi-definite, Q has to be positive semi-definite, and R is positive definite. We know that because of this SQR, this J will never be negative, right? Because these matrices are at least positive semi-definite. So that means what? That means J naught is just the optimal value of this one over here. That means J naught over here is at least 0. It's non-negative 2. If this thing in the common, in the general form is non-negative, then its minimum, of course, is non-negative. That means what? We haven't said anything about the initial state. If this is always positive or 0, that means P, T0, is positive semi-definite, at least. That's a good news, right? We're getting closer and closer to some kind of Lyapunov analysis. This P is getting closer to be a positive definite matrix. Now, this initial time, I can make it 0, I can make it 1 second, I can make it anywhere to start this performance index. So that means if you do consider the entire time interval from 0 to TF, I can select my T0 anywhere in between these two values. And I still must satisfy this P at this T0 initial time is positive semi-definite at the minimum. So that means if you consider this integration from 0 to TF, anywhere inside here, the solution out of it must also be positive semi-definite. That is actually a good news too. So that's saying not only P has to be, if you choose one initial time, P at that time should be positive semi-definite. It says that anywhere, as long as it's less than TF, this P coming out of this optimal LQ problem should also be positive semi-definite. So that's good news. Let's see that in an example, and you will see more. In this example, I do a LQR of a double integral type of system. X dot is, the A matrix is 0, 1, 0, 0, and B matrix is 0, 1. Performance index is as follows. Here, U is a single input. So U transpose R times U becomes just R times U squared, because U is a single input. I'm selecting S to be diagonal 1, 1, So that means in the terminal cost, I am minimizing half of x1 square and half of x2 square. And I'm selecting my Q to be positive semi-definite. That means in here, I am just minimizing x1 square. That's the performance index we are considering. The Riccati equation is as follows. It's just repeating what we did previously. We do the change of variables. We let the boundary condition to be this S over here, identity matrix. A is a 2 by 2 matrix. So P must be also a 2 by 2 matrix. Put them all in here. Q is 2 by 2 as well. Put it in here. Put B inside a column vector. B transpose is a row vector. Put everything in here. And then just assign P star to be this 2 by 2 matrix. We don't put any constraints except that it has to be symmetric. So the off-diagonal terms has to be the same. Then this is just nothing but a bunch of equations related to the derivatives of everything in here. Then we can solve it and then obtain the results. P11 star has to be 1, P12 star has to be 0, P22 star has to be 1. This slide shows that we can actually solve the Riccati equation without a lot of mathematical complications. Any questions in here? From here to here is doing this step. This matrix derivative on the left, we have P11 star dot, and then this is P12 star dot, P12 star dot, P22 star dot. This is the left-hand side. On the right-hand side, just do this matrix multiplications. This P star over here, I won't repeat. This is P star. Just to multiply everything. Multiply everything out. If we have a matrix equation, then each element on the left and on the right-hand side has to be the same. Each entry of the matrix has to be the same on the left and on the right. That's exactly what we have here, where P11 dot equals something in here coming out of this, and then it has a quadratic term about P12 because we have P transpose P. So this quadratic term comes from this product. In here, they won't have any quadratic terms. So that's the spirit of this Riccati equation. The end result is that we can solve the initial value, P11 star at 0. And it looks as follows. We know we have solved the initial time, and we have the Riccati equation over here. We have this bunch of differential equations. I am showing you how this P actually evolves. When R equals to a very small number, this is how P looks like. It has some initial values over here, 1, 1, diagonal terms, and 0, off diagonal. Then it goes through some transient and converge to some values over here. And then we can see that if, this is just repeating the observations, if TF is sufficiently large, actually only after 0.3 second, this P star forward converges to a stationary value. That means P, this matrix that we actually put in the control law, backward converges to a stationary value at P0. That's what we're going to implement, this P over here. A second observation is actually R, if I change different values of R. R is the cost, this constraint in the input. So if I change R to be very, very large, that means I want to penalize the control effort. I want to make use of small U input to control the problem. You can see here, the evolution of P will look like this. It again starts at some initial values. You can see over here, start at 1 and then 0. In the off-diagonal, diagonal terms at 1, it converges as follows. If R is relatively large, then P is going to converge again to some stationary values. So a larger R, you can see, relates to more time that we need to settle to converge to the stationary values. That is intuitive because here we're saying a large R is saying that you cannot give me too big of a U. Otherwise, this term will become very, very large. So if we have a lot of constraint in U, that means we cannot do very quickly at the beginning. So that's why we have a large transient to settle. In plain words, a large penalty on the control input yields a longer time to settle. And now, the final piece, which is quite interesting, is as follows. We finished talking about the influence of R. Let's now look at the other potential variable that will appear in practice. If we fix R, in these two cases, R is the same, but we initialize. We say the terminal cost is different. Here, the terminal cost is identity. We're saying I am minimizing x at terminal cost in this way. In this simulation, I try to minimize the terminal cost a little bit more biased. I say the position actually has more penalty inside. I wanted to have very good position performance, and then I can tolerate a little bit of the velocity at the terminal. The result is as follows. You can see that we initialize the Riccati equations at two boundary values. However, the convergence, although the initial transient is different, but you can see this green line converges in the first case somewhere between 40 and 50. And in here is also somewhere between 40 and 50. Same thing for the red line and for the blue line. Actually, they all converge to the same values in these two plots. So that means the initial value, the terminal cost, actually becomes irrelevant if the terminal time is large enough. Think a little bit about this. We said if the terminal time is really, really long, we want to put the control over the entire time frame. What did we say about the system? We said the system x will have to go to 0, right? Because otherwise the integral will be infinity. So if we know that x will go to 0 in the end, that's why this terminal cost constraint doesn't matter that much. So that's great, too. And these results actually motivate us to go from the finite horizon LQ to the stationary or infinite horizon LQ. Bring back the picture again. The observations we made is that this P in the Riccati equation actually, if the time is sufficiently long, will converge to a stationary value. And in this case, the LQ problem, if TF is very, very large, then P converges to a constant instead of being time varying. So P converges to a constant instead of time varying. The LQ becomes a stationary LQ problem. Because in the control law, remember, control law depends on P. Now, if P for the most of the time is just a constant, then the control law actually becomes a constant eventually. That's actually good news. So that means using just a constant feedback gain, we can actually achieve optimal control. That's the motivation. Here, two more items actually will arise that becomes relevant and brings in our previous concepts actually. It turns out for this stationary LQ problem to make good engineering sense, we just need two conditions. We need AB to define a controllable or at least a stabilizable pair. And AC has to be defining an observable or at least a detectable pair. We're going to discuss about these two conditions and make some sense out of it. Why do we need those? First, the need for controllability or stabilizability. In this performance index, it turns out if AB is controllable or stabilizable, then this Riccati equation will converge to a bounded and stationary value, like what we saw earlier. The demo that I showed you, if you recall, A is equal to 0, 1, 0, 0, and B is equal to 0, 1. This system, AB, defines a controllable pair. We saw the good convergence. The rationale is as follows. If the system is uncontrollable, then there can be these unstable and uncontrollable modes that will appear in this cost function. Some of x will appear that will go to infinity, and then they are counted in this integral over here. And if something here goes to infinity, this integral will go to infinity if TF is large. That's the motivation. And if J becomes unbounded, then this P will be unbounded because the minimum that we can achieve is dependent upon this x0, P0, and x0. Okay? If this goes to unbounded, then J0 will become unbounded. That means P cannot be a stationary bounded value. It's going to have some norms that's infinity. That's a little bit abstract. Let's put it into practice. And when putting this into practice, I would like to give an extreme example. Sometimes looking at things at the boundary will make the analysis immediately obvious. In this example, I have a single input, essentially a 1 degree of freedom system. I make B to be 0. And in this way, there's no way that the system is going to be uncontrollable, right? B is 0, then the system is entirely uncontrollable. X is just going to evolve based on the initial condition of 1 is going to become unbounded. This integral is going to become larger and larger and larger. X goes to infinity in the end. I can say Q to be 1 and R can be any positive value. Doesn't matter. The system, the result is going to become yield conditioned anyway. The system is uncontrollable, and the uncontrollable mode here is unstable. X will keep increasing to infinity based on actually the exponential convergence. EAT, A is 1 times T, and then X0. It equals ET, given this initial condition over here. So X goes to infinity. If we look at this one over here, this integral, if TF is large, then you do this integration, this will become unbounded, however hard you try in your input. Okay? No matter how hard you try, this is going to be infinity. And in this case, look at this Riccati equation. We're going to show that Riccati equation by this, in this problem, this P will go to infinity. It cannot converge to a bounded and stationary value. Just look at it. We have negative P dot, P, A transpose P, PA, right? A is 1, so it's P plus some quadratic term about P over here. And inside, it depends on the input U. let's just copy it this way. Bring this one more time from here. Over here, this Riccati equation is reading as follows. A transpose P, A is 1. PA is equal to P again. Q is 1 in my problem. And inside here, it's some quadratic term about P. And it depends on B. And in this example, what is our B? B is 0. So this term goes away completely. So that's why we have this Riccati equation reduces to negative P dot equals to 2P plus 1. Or if we use the change of variables, it's saying that dP star equals to 2P star plus 1. And we have some initial value for P star, which equals to S at the initial time. You can see here, no matter what S is, we can see that this integral, if we do forward integration, P star is going to go to infinity. That means P, from this solution, if we integrate P backwards in time, P0 will become infinity. So the P in here, the Riccati equation, doesn't converge to a bounded and stationary value. So that's a counterexample, demonstrating the need for controllability and stabilizability. The second piece is observability, which is also intuitive. Turns out, if AC is observable or detectable, then the optimal state feedback control system will be asymptotically stable. That's the need for observability. To see that, you can see that if AC is observable, then this quadratic term inside this integral, we have X transpose CX. Observability means that this output, we can actually reveal a lot about the state from the output. We can completely define the initial value of the state because it's observable. So that means if we do this regulation, a lot of the state information will be contained inside this integral. Then that means our objective, our performance index, actually counted for the states very comprehensively. And more formally, the result is as follows. If AC is observable or at least detectable, then the solution of the Riccati equation will converge to a positive, at least a semi-definite value. P, we call it P subscript plus. That's reviewing our example where we saw that the P converges to some stationary value. And all those numbers, if you recall, actually positive in the diagonal elements, and actually 0 in the off-diagonal elements. The proof of this statement is provided in the course pack. Intuitively, we need this controllability and observability for this infinite or stationary LQ to make sense. In a summary, here is the main equations as well as results for LQ and stationary LQ. In the LQ problem, the performance index has a terminal cost and the integration is finite horizon. In the stationary LQ, there's no terminal cost, the integration is infinite horizon. The system dynamics, if it's a regular LQ problem, not stationary, infinite horizon, then we don't need the controllability and observability. But if we think about the problem in an infinite horizon, then the conditions are a little bit stronger. We need controllability and observability. The Riccati equation, if the time is sufficiently long and P converges, then this left-hand side becomes 0. And we only have this algebraic equation. There's no derivative of P. It's A transpose P plus PA minus this quadratic term about P plus Q has to be 0. And then the optimal control law in the LQ problem is time varying. In the stationary LQ problem is time invariant. The cost, optimal cost, they have the same structure. The infinite horizon LQ is actually good. It's actually not only well formulated, but also it has easy solutions in the end. The formal statement is as follows. For this infinite horizon performance index with Q equal to C transpose C, system dynamics over here, initial value, and a positive definite R. If AB is controllable or stabilizable and AC is observable or detectable, then the optimal control input is provided by this constant state feedback law. The gain is dependent upon your cost in the input R, the B matrix, and then the P matrix coming out of this algebraic Riccati equation, or ARE in short. And the performance index designed this way will make the closed loop system to be guaranteed asymptotically stable, with the minimum cost to be dependent upon the initial time and P plus. All right? This is very strong conditions. Throughout the entire analysis, we actually didn't do any eigenvalue analysis. We didn't do a Lyapunov construction. But in the end, it's guaranteed the closed loop will be asymptotically stable, which is actually really nice. Let's do some observations which repeat some of our analysis. First, this is a constant state feedback law. And second, under this constant feedback law, plugging U equal to this into AX plus BU, then we have the closed loop A matrix is A minus B R inverse B transpose P. And then the performance index J, we can plug in this U again over here. U is a constant feedback, state feedback. So this is actually a quadratic term about X too. And if you plug in here, you can combine these two quadratic terms about X and have X transpose Q plus P B R inverse B transpose P. Just plug this inside here. So, in a sense, we now have the system becomes, under this optimal feedback law, becomes this, with a performance index that look like this. Now, look at this one. Does it sound familiar to you guys? We have seen this, something similar to this before. When we did the Lyapunov analysis, isn't this what we experience all the time? We have something about x dot equals ax, and we have a performance index. We have a j that's equal to x transpose qx in this integral. This one, we can actually do a Lyapunov analysis, right? For this system, if we can solve a Lyapunov equation, AC transpose P plus PA plus QC equals 0, and this P coming out of it is positive definite. That means what? We have Lyapunov stability, right? And guess what? This is precisely what we have in this Riccati equation construction. You can see here, this is what I want. If we put this AC, this thing inside here, plug in AC, plug in QC in here, then we have A minus B R inverse B transpose P transpose times P plus P times this AC, put it in here, equals negative QC, negative Q minus this quadratic term about P. Just look at this, and then you can actually recognize that this is nothing but the Riccati equation. We have A transpose P, we have PA, we have Q, and then on the right-hand side, we have negative PBR inverse B transpose P. On the left-hand side, we have two of these. We have negative PBR inverse B transpose P in here. Here, this transpose times P will generate P transpose times B times R inverse times B transpose times P. Here, in this product. P is symmetric, so P transpose equals P. And R is positive definite, so R is symmetric too. Its transpose, it equals itself. You can see we have this term appearing both on the left and on the right, so it's going to cancel itself. And then we have a remaining term, P, B, R inverse B transpose P, P, B, R inverse P transpose P. Do this substitution, and you will recognize that this, in the end, is actually just a Riccati equation. Now let's flip the logic. This Riccati equation is by construction. We solve the problem, and then we said we have P that satisfies this Riccati equation, right? So that means the Riccati equation is automatic out of the LQ problem. So that means this is also automatic out of the LQ problem. In other words, throughout this analysis, we implicitly have a Lyapunov equation for this closed-loop system. And that is why we have the asymptotic closed-loop stability guaranteed. That's the intuition. So which is good. When the Riccati equation is positive definite, then this half of x transpose P plus x is a Lyapunov function for the closed-loop system. All right. Here, I just summarized it in a table. These two are actually equivalent. We started with this system and this performance index. But after we solve the system, we plug in this optimal control law, it actually becomes this closed-loop dynamics, x star equals ACX. And the performance index is actually just nothing but x transpose QCX in this integral. The full picture of this, there are a few more elements that I won't go into the details. The course note also provided additional analysis over here. So we have the guaranteed closed-loop stability, which is very attractive. And the LQ, the stationary LQ, actually has other nice properties too, not just the assured stability. Before we see that, before I provide you those nice properties, let's take a look at the example again. This time in a infinite horizon setting. Same kind of A and B matrices. Then cost function Q is positive semi-definite, R is positive, single input system again. We just solved the algebraic Riccati equation. So we have A transpose P plus PA plus Q minus a quadratic function, quadratic term about P that depends on U, depends on R, and depends on U, B transpose. If we say, do the similar analysis, if we just assign P to be P11, P12, P12, P22, and then plug in to here, we will have a function about the entries of the P matrix, which we can solve. The result is that P has to be this symmetric matrix. Depends on R over here in this way. The A matrix, the closed loop A matrix, will become, now just to substitute the control law inside here, becomes A minus B R inverse B transpose P star. You can compute, it becomes this. So the closed loop depends on R. Depending on how much you constrain or limit the input magnitudes, the closed loop will behave differently. In particular, we can analyze the eigenvalues. Let's take a look at how, if I change the number of R, how the eigenvalue will evolve. The eigenvalue coming out of this A matrix, A closed loop matrix, is a pair of complex numbers. If we increase R, then you can see this eigenvalue will evolve more towards the origin if R is large, if R increases. If R increases or we put more penalty on the control input, then the eigenvalues will move closer to the origin. We'll have slower convergence of the state to 0 if eigenvalues are closer to the origin. If R reduces, then this eigenvalue will move further away from the origin if R reduces. That's saying that if we don't put a lot of penalty on the control input, we allow for large control efforts, then eigenvalue move further away from the origin. That means the closed loop dynamics is faster. That means the convergence of the error will be faster. So that's intuitive. If you allow me to put more controls, then I can make the system converge faster. So those are makes intuitive sense too from the closed loop eigenvalue viewpoint. In MATLAB, the commands related to the infinite horizon LQ problem is as follows. CARE computes the continuous time ARE, i.e. continuous time algebraic Riccati equation. You substitute in A, B, Q matrix, R matrix, then it will tell you everything you need to implement the control law. It will tell you P, it will tell you K, the feedback gain. It also tells you the closed loop eigenvalues, lambda. You can also use these commands, LQR, LQ regulator, or LQRY, which takes similar inputs. For LQR, it takes A, B, Q, and R. It spits out K, P, lambda. And for LQRY, this solves the problem if the performance index explicitly is written as a function of y in this transient cost. And then in that case, you just feed your system, state space system, into the function, feeding this qy and feeding r. It's going to tell you the feedback gain, the Riccati equation solution, as well as the eigenvalues of the closed loop systems. So quite convenient. You don't have to always use the in-hand, by-hand calculations. I would like to conclude the LQ problem by mentioning that not only it has guaranteed closed loop stability and minimizes the cost, it also holds some other nice properties. It has good robustness too. It has the robustness of at least 60 degrees of phase margin. It has infinite gain margin for the closed loop system. And stability is guaranteed up to a 50% reduction in the gain too. In practice, you need to define for the stationary LQ problem. You need to define these two. You need to tell it what kind of R, what kind of Q you want to put in the performance index. If there's no idea about the structure of Q and R, start by making diagonal matrices for Q and R, just like what we did in the example. And if you know a good idea of how the the magnitude of the state, if you know, for example, the unit for the position and velocity, you have some idea how far the system will travel. Then you can design Q and R utilizing these boundaries of the states and inputs. More specifically, if you know the maximum of the states, then you do the diagonal elements of these to be inversely proportional. So in other words, do something like this. Q to be 1 over K1 over X1 maximum absolute value. And then do the same for other states. Make Q to be in this way, inversely proportional to the maximum of the states. And then do the same for R to be the maximum, to be inversely proportional to the maximum of the input command. Doing it this way, in an intuitive sense, normalizes everything in your quadratic function cost.